previous two slides. So well, network drivers can be exploited not only remotely but also locally. There are a number of vulnerabilities that allow local privilege escalation and getting the kernel mode privileges to the attacker, to the user mode applications. Most of those vulnerabilities are in the device IO control local API. That is common to all the Windows drivers, and we'll describe briefly these kind of vulnerabilities. IO control codes is a common interface between mini-port drivers and upper-level protocol drivers and user mode applications, which is more important to the attacker. On Windows, applications called device IO control function, Win API function, with the IO control code of an operation that mini-port driver should perform. So therefore, the application, user mode application, can control the device using this IO control interface. IO Manager Windows Executive passes major function device control down to the driver in response to this code received. The IO control defines a method used to transfer input data and to the driver and output data from the driver back to the application. The methods are buffered IO, direct IO, and neither IO. And actually, the vulnerabilities may be common to all of these data transfer methods, and but also may differ significantly from one method to another. So NDIS is a framework for drivers managing network cards, basically for network drivers. NDIS defines object identifiers for each piece of configuration or statistics that an application can query or set to the driver. So as a common communication path, device IO control interface represents a common way to exploit kernel if a driver fails to correctly handle the IO control request. Or, for example, some of the object identifiers sent within this IO control request. So, to exploit the IO control codes, specifically network drivers and these drivers, an attacker should identify a correct object identifier that the driver fails to process correctly. In some cases, even the invalid object identifiers can also be exploited, and it is given in this example. So the driver copies unchecked contents of the input buffer into the internal buffer even before validating the object identifier, even before dispatching it to the query OID function. So the user mode application, malicious application, can send object any trash instead of object identifier, and this will trigger this vulnerability. So how to force the device IO control API? First of all, we'll need to find a target device name. For example, enumerate objects in device object directory of Object Manager Executive namespace. Use tools such as WinObjects by 4F, Device Tree, or WinObj. Network cards can also be enumerated using getAdapter info Win API. Then the attacker, the fuzzer needs to generate IO control codes. The fuzzer can use control code macro based on the device type, method access, and function fields. Device type is known from the device object. Each device type can have a set of common IO control codes, and these common IO control codes can be simply hard-coded into the fuzzer, for example. But the network driver can also, or any other device driver, can support any proprietary IO control code, and it can fail processing them correctly as well. So the fuzzer needs to discover these IO control codes as well. So the proprietary IO control codes can be fairly easily generated, fairly cheaply generated. Method and access fields are almost fixed. They have 1, 2, or 3, sometimes very rarely 3 values. Function is within the range of 800. Below 800 is reserved by Microsoft, and between, for example, 810 in hex, so at most 16 private IO controls, or maybe 128 IO control codes. So it's not necessary to generate all the 4 gigs of IO control codes. So then the fuzzer needs to, for NDs, for network drivers, the fuzzer needs to generate object identifiers. It can be used by by sending OID gen supported list to get supported object identifiers. So basically, driver advertises the list of all object identifiers it supports. But the problem is that the driver again may support object identifiers, proprietary object identifiers that it doesn't advertise at all. So it will not return in response to the gen supported list request. So the fuzzer needs to generate them as well. So it is also fairly easy to do, actually. So the two most significant bytes are discovered using the gen supported list, and they are fixed across all the object identifiers supported by the drivers. And the least significant byte can be fuzzed within the between 0 and 255. So this is the automated method of discovering IO control codes and object identifiers. But it is possible for attacker, for example, to identify all supported object identifiers and IO control codes fairly easily by reverse engineering the binary of the driver. I will explain that in the next slide. OIDs are supported by NDs mini-port drivers, by network drivers only, but we have we have lots of other types of drivers. And for example, I will not cover this example here, but for example, for storage mini-port drivers like SCSI drivers, the fuzzer needs to generate in the same fashion the SRBs instead of object identifiers. And finally, the fuzzer needs to vary the length of the input and output buffers, the sizes of the length of these buffers. To reduce this pace, the fuzzer may vary input and output buffer sizes around the size of the structure expected by the driver for a certain object identifier, and within the fixed set. 0 for -1. 4 it's the length of the object identifier. That's why some of the drivers, especially prior to NDs 5.1, they actually expect the length of the input buffer to be 4. Otherwise, they fail the request fairly early. So. I explained that it is possible to reverse engineer the binary of the driver and to identify the supported OIDs, because processing OIDs is typically done within the huge switch in the code, which is compiled into the jump tables. And it is this example of FIDE Pro screenshots gives a way to identify all general NDs 802.11 OIDs in the wireless LAN driver binary. I will jump over this slide and actually describing this in more details in the white paper. So we fuzzed mostly IO control codes, object identifiers, probably SRBs, and the lengths of the buffer. But we didn't fuzz the contents of the buffer. But actually, to have it's not a completely dumb fuzzing, but it's not also the very like smart fuzzing, because to make a fuzzing of device IO control API more smarter, it is not enough to fuzz only the sizes of the buffers. For each object identifier. Sometimes it is enough, but in many cases the fuzzer must be aware of the structures it is passing to the driver. Simple example, the driver may copy SSID length bytes from SSID into 32-byte long buffer in response to OID 802.11 SSID object identifier. If the fuzzer sends input buffer with the SSID less or equal than 32, then the overflow doesn't occur. Hence, the driver should be aware of that field, of that specific byte in the input buffer, which is SSID length. So that shows that the device IO control fuzzer needs to understand the structures it is passing in the IO control request for a certain object identifier. Most of these techniques we implemented in the proprietary IO control fuzzing tool, IO control BO driver security testing tool on Windows. And there's some information in the white paper for this tool. Couple of words about the state of the device and the driver. Device state matters. Examples: if the malicious application, for example, or a fuzzer sends OID 802.11 SSID, this is the request that wireless LAN mini port needs to return SSID of associated access point. So what if this station is not associated to this access point? The vulnerability is not triggered, even if it exists. OID 802.11 add key. Have station used a new web key. The vulnerability is encountered when a station is associated with some access point with web encryption. But it may not be triggered if there is an open system non-authentication encryption, or the access point supports WPA cipher suits, or the station is not connected at all again. OID 802.11 BSSID list. This object identifier is used to request the mini port driver, wireless LAN driver, for the information about all BSSIDs detected by the station. Actually, the information not about just BSSIDs, MAC addresses, but the information about a whole bunch of information about all the WLANs discovered by the station. So the vulnerability, even if it exists, it may not be triggered if there are no wireless LANs in the range of station or the radio is off. Then the driver may support the proprietary MyDRV log current WLAN object identifier used by an application to obtain debug information about the associated access point. Again, what if the station is not associated with any access point? The vulnerability is not triggered. So the three major states defined by the original 802.11 specification based on the authenticated and associated states are not enough. The tester may consider the following additional states to fuzz the wireless LAN driver, and in each of the states, the vulnerability may be encountered. All right, so we have discussed the vulnerabilities in the device IO control API which lead to local privilege escalation. And it's currently believed that they lead to local exploits only. But it's not true, and I will show you why it is so. So the next section covers remote exploitation of these IO control vulnerabilities. So local or remote. IO control vulnerabilities are less severe than remote because they are exploited by local user land exploit code. This is wrong, because IO controls are used to curate driver for information that WLAN driver receives mostly from the frames, from the outside. For example, detected BSSIDs, current SSID, rate supported by the associated access point, WPA information, and so on. So what will happen if the local IO control vulnerability occurs when returning this particular information? The vulnerability depends on the data supplied by the attacker remotely, and it can be exploited remotely. But an attacker needs to have a local agent that will send vulnerable IO control request with the vulnerable object identifier. It's a disadvantage for the attacker, so it still makes the vulnerability local because it should have a local code. It's not true. Any network management application, for example, wireless management application that you have on your laptops, or even a protocol driver,